Hi everybody. I'm going to do problem 71 from chapter 8. So this is from chapter 8 here. And it says block 2. So this is block 2. This is block 1 here. You can see half Atwood machine. You've seen these before. But now we're going to use these basically with energy. So it says block 2 is shown below along a frictionless. So it is frictionless. I don't have to worry about friction. Table as block 1 falls. Both blocks are attached by a frictionless pulley. Find the speed of the blocks after they've moved 2 meters. So they move 2 meters. And they're attached to each other, so if block 2 moves 2 meters, that means then block 1 also moves 2 meters. So, yeah. So it says, assume they start at rest, okay, and that the pulley has negligible mass. So that basically means we'll worry about that when we get to rotation. So, so that's rotational dynamics, by the way. So we're going to say use M1 is 2 kilograms, M2 is 4 kilograms. So what I'm going to do, I did this during office hours today, and I had a really good conversation, and we did this problem multiple times, and what's great is, no matter which way you look at it, you still get the same answer, which is great. So I'm going to look at this multiple ways. One of the first ways is to kind of look at these individually. Well, kind of individually. I'm still going to use the conservation of energy, though, with the idea that the only non-conservative force acting here, well, there's 3 non-conservative forces. So if I were to draw a free body diagram acting on 2, I'd have the normal force acting on 2. I would have the weight acting on 2. I would have the tension force acting on 2, and that would be it. And then the same thing here, I would have the weight of M1, and then I would have the tension force as well. That's let's just call it T, Ft, right? Both those tension forces are the same. And we know the displacement is going to be this way, right? The displacement is going to go this way. That's going to be the displacement of mass 2, and mass 1 is going to have the exact same displacement. So the tension forces are the same. We know this because they're in the same rope. It's a massless pulley, etc., etc. We've done this multiple times. The tension forces are the same. But here, the work done by the tension force, which is a non-conservative force, but the work done by the tension force is positive with this displacement. And then the work done by the tension force here, they're pointing in opposite directions, so it's going to be negative. So basically the work done by the tension force on object 2 is going to be opposite the work done by the tension force on object 1, and they're going to cancel out, so I don't really need to worry about the work done by the tension force there. So both the gravitational forces, those are conservative forces. I don't need to worry about them. The only other non-conservative force I need to be careful of, because again, if I have a non-conservative force, I would go to this work done by a non-conservative force is equal to the change in energy. Again, on your equation sheet, I think it just says work is equal to your change in energy. If I have a non-conservative force doing work, then I got to kind of default to this equation. But if that's not the case, if the non-conservative force does 0 work, then I get that the work done is the final energy minus the initial energy, and that leads to the conservation of energy, right? Okay. So let's look at that. Oops. Let's look at that, because the only other non-conservative force I have working here is this normal force, but the normal force is perpendicular to the displacement, and anything perpendicular to a displacement is going to do 0 work. So I don't need to worry about any of the non-conservative forces, basically. So the energy is going to be conserved here. So I am going to use conservation of energy, that the initial energy is going to equal the final energy. But I'm going to look at this multiple ways, and I'm going to see that I'm going to get the same answer no matter what. So I'm going to say that this is my 0 mark. So here's the thing with energy, is that you have to pick a 0 mark. What do I mean by that? Well, if I have my cell phone up here, right, and let's say my cell phone, and then I make my 0 mark the ground, so my cell phone is up on the table. It's at the edge of the table. So my cell phone is at the edge of the table here. And let's say that the potential energy that I calculate here the gravitational potential energy is 20 joules of potential energy. Right there. So it's at some height, right? It's at some height. So I would say, oh, because this is my zero mark. This is what I'm calling my zero mark. And it matters what you call your zero mark. So, okay, when the cell phone's up here, it's got 20 joules of potential energy. But then I take my cell phone and I bring it down here. And at the end here, the final energy is going to be 0 joules of potential energy. So then I could say, okay, what's the change in gravitational potential energy? Well, that's going to be the final gravitational potential energy minus the initial gravitational potential energy. Well, that's going to be 0 minus 20. So my change in gravitational potential energy would be negative 20 joules. That's negative 20 joules right there. So I'm going to do the exact same thing. But I'm going to do it over here. And instead, I'm going to change my zero mark to be here. So now here's my zero mark right at the table. My zero mark is at the table. So my initial then gravitational potential energy is going to be 0 joules, right? Because it's at my zero mark. The height is 0. The distance, the elevation above my zero mark or below my zero mark is 0. So therefore it's going to be 0. Where if I look then at the final gravitational potential energy, where the cell phone ends up, well, that's below my zero mark, right? Below my zero mark, so it's going to be negative 20 joules, right? It's 20. It's below my zero mark. It's just the same way that if I said if I got 0 degrees below 0, that's negative 20 degrees, like I don't know, Celsius or whatever. That's negative 20 degrees. So then, what's my change in gravitational potential energy? Well, change in anything is the final minus the initial. So that would be the final is negative 20 minus the initial, which is 0. So my change in gravitational potential energy is also negative 20 joules. So here's the thing with energy and why not all energy, but gravitational potential energy is particular about this. What's more meaningful? The more meaningful thing when it comes to gravitational potential energy is the change in gravitational potential energy. Because the change is always the same. Both of these situations show the change in gravitational potential energy is negative 20 joules. However, the initial potential energy is different. The final potential energy is different. And that's because you get to choose where your zero mark is. You get to choose where 0 is. So if somebody told you, oh, the gravitational potential energy is 100 joules, you might say, okay, with respect to what? Right? What are you talking about? In order to then find out exactly what they mean. But if they say the change in gravitational potential energy is 100 joules, well, okay, that makes that then is going to be agreed upon no matter who you are and what you talk to. What am I talking about? All right, trying to move right along here. So let's try this again. So I'm going to say my zero mark is right here. This is where I'm going to start here. My zero mark is right here. And so what I'm going to start with is I'm going to treat all these kind of individually with the assumption that the tension force is doing no work. So I can use the conservation of energy. So my question is, okay, for each one of these things, what's the initial energy? What's the final energy? So, and we're going to say, here's the initial moment. Here's the initial moment when everything is set up the way it is. So that's the initial moment. And then the final moment is when block 2 is over here, right? Block 2 is over here. And then block 1 is down here somewhere, right? Block 1 is down there. So that's kind of the final moment there. So, okay, what do I want to do? Let's take you and move you here. That should be okay. All right. So, yeah, that's then my final moment right there, where this thing goes a distance. This thing goes a distance like this, and I'll call that distance y. So because I'm calling it y because the first thing I'm going to say, okay, what is my energy energy here for object 2. So this might seem a little silly, but I'm trying to prove a point. So my energy for object 2 initially is going to be, well, my energy for object 2, well, let's see, it's some height above the ground here. So it's at some height I'm going to call h above the ground. So I got then gravitational potential energy. So that means I have gravitational potential energy initially, but both these objects initially are at rest, so there's no kinetic energy. So that's it. Object 2's initial potential energy is that. And then the initial potential energy of object 1, though, is, so let's just go ahead and say we have potential energy of object 1. So how do I want to do this? Let's just say the initial total energy of this whole system. So the initial total energy, well, object 2 is going to have gravitational potential energy initially. So that's object 2, initial gravitational potential energy of object 2, plus the gravitational potential energy of object 1, let's say, right? Even though object 1 is at my 0 mark, so we know this is going to be 0, but we're just going to say that that's the case right there. Okay, so there we go. We got that right there. That's the initial energy. So for our final energy, well, there's going to be, well, the object is dropped below here. So, well, let's see. We got object 2 is still at the same height, right? So the final potential energy for object 2, so I'm going to have gravitational potential energy for object 2 at the end, plus gravitational potential energy for object 1 at the end. Plus object 1 is now going to be moving, so both object 2 and object 1 are going to be moving with the same speed, right? They got the same speed because they're going to be connected to one another. So I would have kinetic energy from object 1 at the end, plus the kinetic energy from object 2 at the end. Yeah, let's just throw all this at the bottom here. So I'm going to say, all right, now I'm going to use this conservation of energy idea. The total energy of this system, where this is the system here, but I'm basically breaking it up into individual parts and adding them up. Well, the total energy of that system is going to be my initial energy, which I got up here, which is the gravitational potential energy of object 2 at the beginning, plus the gravitational potential energy of object 1 at the beginning, which is going to equal the gravitational potential energy of object 2 at the end, plus the gravitational of object 1 at the end. Sorry, it's object 1, not initial. Plus the kinetic energy of object 1 at the end, plus the kinetic energy of object 2 at the end. All right, let's look at this. So the gravitational potential energy of object 1, remember, gravitational potential energy is mgh. So gravitational potential energy of object 1, well, it's at my 0 mark, right? So h is equal to 0 for object 1. So for object 1, if h equals 0, well, then all of this is just going to be 0. It has no gravitational potential energy right here. And then what about the change in height? So let's look at here. What about the change in height for object 2, right? Because again, gravitational potential energy is mgh or mgy, right? Any of those things. Well, the mass of object 2 doesn't change from here to here. The gravitational field doesn't change, and the height doesn't change. So this is also going to cancel out, right? Or not that they equal 0, but both of these things cancel out, right? Because if I had 2 on this side and 2 on this side, those 2's would just cancel out and just subtract both of them. So that's going to leave me then with 0 equals the gravitational potential energy of object 1 at the end, plus the kinetic energy of object 1 at the end, plus the kinetic energy of object 2 at the end. So, all right, 0 equals, what's my gravitational potential energy at the end? Well, my gravitational potential energy is below my 0 point. Remember, my 0 point is here, right? My 0 point is there. So it's below my 0 point, so that means I have negative gravitational potential energy. So I really should have written this as negative right there. So it's going to be negative mgh, and that's m1gh because we're talking about mass 1, plus kinetic energy is 1/2 mv squared, so it's m1v squared plus 1/2 m2v squared, right? Because these speeds are going to be the same, like we said before. Okay. So then that's going to be then I could add m1g to both sides. That'll give me m1gh equals, and then I can factor out this 1/2 and v here, because that's going to give me 1/2 m1 plus m2. That's m1 plus m2. I'm factoring out the 1/2s and the v's because those are all the same. So v squared, and then I can get the speed. So it's going to be multiply both sides by 2 and divide by m1 plus m2. So I'm going to get 2 m1gh over m1 plus m2 equals v squared. And that'll give me 2 times mass 1, which is mass 1 is 2, mass 2 is 4. So mass 1 is 2, mass 2 is 4. So it's going to be 2 plus 4, 10, and then the height is, what's the change in height? 2? 2 meters. Change in height is 2 meters. So it's 2 times 2 times 2, which is 8. So times 10 is 80 divided by 6. Oh, square root. So, right, got to take the square root of both sides. I'm about to say that's not right. So take the square root of that, 3.65. So my speed is 3.65 meters per second, and there I go. So that's one way I could do this. All right, let's look at it a different way. The different way is going to be, I'm going to say, instead, I'm going to look at this whole thing as one system. So I'm going to look at this whole thing as one system, and I'm going to ignore this height, right? Because I could look at this and go, well, block 1's going to go from here to here. There's no way there's going to be any change in gravitational potential energy, so I don't really need to worry about it. So I don't need to worry about it. So what I'm going to do instead is not worry about block 2's change in gravitational potential energy, and I'm going to look at the whole thing as a system, and I'll do the same thing again. But I'm going to keep this right here, because then I'm going to simplify it to the way that I ended up doing this. So I'm going to continue to say this is my 0 mark right here. Did I say H? Oh, shoot. I should have said this was Y, right? Sorry. This was Y. Because I ended up saying that was Y. Yeah. Right, because I called that Y. Sorry about that. So, okay. So instead now, again, I'm not going to worry about this change here because there's no change in gravitational potential energy, so I don't really care about that. So at the beginning then, here, if I look at initially, well, both blocks are at rest, and block 1, which is the only thing that's going to drop, is at my 0 mark, so that doesn't have any gravitational potential energy either, so the initial potential energy then is going to be 0. But then both blocks drop, so it goes, or not both blocks, block 1 drops, and block 2 starts to move, so block 2 now has some kinetic energy, block 1 also has kinetic energy. So I'm going to say at the end, I've got negative gravitational potential energy for block 1, right? But then I'm going to add that to the total kinetic energy at the end, right? Because both blocks gain kinetic energy. Basically, the potential energy that block 1 loses turns into kinetic energy. I'm sorry, the potential energy that block 1 loses is equal to the kinetic energy that both block 2 and block 1 gain, right? That's kind of the idea that I'm getting at here. So let's see what that looks like with the conservation of energy. My initial energy is equal to my final energy. Let's take you and bring you over here. I'm going to do it one more time. So it's going to be 0 equals my negative gravitational potential energy for object 1 plus my total kinetic energy. So that's going to be equal to 0 equals mass of object 1 g times y. That's the height change right there. Plus my total kinetic energy, that's 1/2 times the total mass of the system, which is going to be m1 plus m2 v squared. Sorry, it's negative there. So this is going to be then m1 gy equals 1/2 m1 plus m2 v squared. If I isolate all this, I get 2 m1 gy over m1 plus m2. Take the square root, and that's going to be my final speed. And if I look, 2 m1 gy over m1 plus m2, that's exactly the same thing that I got previously, so I'm going to get the exact same answer. So we're going to look at this one more way. So that's another way to look at it right there. So we're going to look at this one more way, which is instead now I'm going to move my 0 mark to the lowest point that mass 1 reaches. So this now is my 0 mark. So here's my 0 mark. Okay, again, block 2, I don't care about the change in energy. Right? I really don't care about the change, or not the change. I don't care about this thing, sure, okay, it does have gravitational potential energy because it's this high above, but it's the same height above the next time, right? So who cares about the change in energy? So I'm just going to say its initial energy is 0, right? The initial energy is 0, but then it gains energy later on, but that's at the end, right? So with this one here, there's gravitational potential energy for object 2, right? Object 2 is at a height now y, so I do have, and it's above, by the way, it's above my 0 point. So I do have gravitational potential energy for object 1. Sure. So I got gravitational potential energy for object 1. And then for object 2, or I'm sorry, for the end, for the final energy of everything here, that basically what's going to happen is the potential energy from here is going to turn into kinetic energy for here, right? Because now object 1 reaches the 0 mark, so the potential energy is 0. So I don't really care about that anymore. So the potential energy is 0, so all I have now is my total kinetic energy at the end. Well, okay, now I'm going to use the conservation of energy. My final energy is here, my initial energy is here. Let's try it out. So I'm going to have my initial energy is equal to my final energy. My initial energy was gravitational potential energy from object 1. And then my final kinetic energy, well, that's the total kinetic energy at the end. So this is going to be m1 gy, which is going to equal 1/2 m1 plus m2 v squared. So lastly, I'm going to isolate v squared. It's going to be 2 m1 gy over m1 plus m2, take the square root, and again, it's exactly the same thing that I get here and the same thing that I get down here. So all 3 ways work, and honestly, there's even more ways than what I just showed you here, but I just thought I would show you that because it's kind of cool to show you how energy, no matter what you do, as long as you stay consistent, will give you the same answer. All right, bye everybody.